thanks for joining me for this. We're going to be talking about permutations and combinations. So in a previous video, we discussed the counting principle. We're going to get a little bit more complicated now, where we're going to be talking about the importance of order and formulas we can use depending on the situation. So a permutation is what we will use if order matters. This is kind of related to the counting principle. We saw some examples where we had people competing in an event and they were going to be placed gold, silver, and bronze. So they were going to be getting medals. And the order matters because it makes a difference if you get the gold medal versus either of the other medals. So order matters. When order matters, you're going to use permutation, and the formula is given right here. So this is the permutation of n choose r. So you have n items. So you have n items or n choices, and you're choosing r of them. Okay. So that would be like if you had 31 contestants and you're going to choose 3, right? You're going to choose 3 winners, a gold, a silver, and a bronze. So n would be 31 and r would be 3. We saw that from the previous video when we talked about counting principle. So if I go back to that, let me just work through that. If we have 31 competitors and we want to fill the podium with 1 gold, 1 silver, and 1 bronze medal winner. We have 31 competitors, so there are 31 people who could possibly win the gold. Well, after that person is chosen, there are only 30 people left that could possibly receive the silver. After gold and silver are both chosen, then there's only 29 possible options for the bronze. And so we found the answer to this by multiplying the numbers together, 31 times 30 times 29, and we got 26,970. So in this example, we can really just kind of think through it, use blanks, and use the counting principle to figure it out. But the other way you can do it is, let's see, I'm going to make sure I put these details here. Is to decide if order matters or not. And so if you have 31 competitors with 3 winners, and the 3 winners are specifically in a place, right, gold, silver, bronze, or first, second, third, then what you would do is you would use a permutation. Let's see how this formula works. So this is a permutation because order matters. There are places, right? N means how many you have a choice to choose from. So we have 31 competitors, and R stands for the number that you're choosing. So we're choosing 3 winners. The formula is n factorial. So remember that the first number is n and the second number is r. So we're going to put in n factorial, so that's 31 factorial, over n minus r. So that's 31 minus 3 factorial. Okay, so let's see, we have 31 factorial over 31 minus 3 is 28. So 28 factorial. Now let's see what that really means. 31 factorial, remember, is 31 times 30 times 29 times 28 times 27, and it keeps going, right? All the way down to 2 and 1. 28 factorial means 28 times 27 times 26, all the way down to 2 times 1. So since we have all multiplication on top, all factors, and all multiplication or factors on the bottom, we're able to cancel out common factors. So the 28s would divide out and make 1s. They would cancel. 27s would cancel. All of them, right? 26 would cancel, 25, all the way down to 2 would cancel, and 1 would cancel. So the only thing that's left is 31 times 30 times 29, which is exactly the same thing, if you notice, that we did up here. And so this formula is taking into account the fact that you're choosing 3 winners in an ordered way, and you'll get the same answer. So now let's look at a combination. A combination is when order does not matter. So it doesn't matter the order. So it might be you have 31 competitors and 3 people are going to win, but there's no value in first, second, or third. It's just 3 people win. So maybe it's like a door prize. They have 3 gift cards and they're going to randomly pick 3 people to win the gift cards. And it doesn't matter if you're picked first or if you're picked third. Either way, you're going to get a $50 gift card. So order doesn't matter. You're just picking 3 winners out of, let's say, 31 people that attend an event. And so then you will know to use the combination. If you look at the combination, the formula is very similar. You will see that the n factorial on the top is the same as the permutation, and the n minus r factorial is the same as the permutation. So that part is exactly the same. But you have the addition of this r factorial on the bottom as well. So you're multiplying the permutation formula by an r factorial in the denominator. That's the only change to the combination formula. And what that does is it takes out the repetition. So since order doesn't matter, let's say you pick person A, person B, and person C. Person B, person A, person C. Those will be the same. Those are the same if order doesn't matter. They're all getting the same prize. But if you have a gold, silver, and bronze, the order that you select them in does matter. So for the combination, there's going to be fewer combinations to make rather than permutations. So the number, if you're using the same numbers, the number will be smaller. So let's use similar numbers that I just did for the permutation. Okay, so that's permutation. Okay, let's do a combination. Okay, where we have, let's say we have 31 people attending an event, 31 attendees, 3 people will win a $50 gift card. So it doesn't matter if you're the first person to win a gift card or you're the third person to win a gift card. Either way, you're getting the same dollar amount of a gift card. Again, this will be different if, let's say, the first person gets a $100 gift card and the second person gets a $50 gift card. Since the value of what you're winning is different, then order would matter, right? But if they're all getting the same gift card, order does not matter. Okay, so let's use the formula. We're going to have a combination this time because order does not matter. 31, choose 3 winners. So it'll be 31 factorial over n minus r, so 31 minus 3 factorial times r factorial, so 3 factorial. So we know 31 minus 3 is going to be 28. We saw that in the previous one. Okay, so what we're going to do here is we're going to write 31 times 30 times 29, and I'm going to keep going until I get to the larger of the 2 numbers on the bottom. So in the denominator, the larger number is 28. So I'm going to keep writing my multiplication on the top until I get to that number. And once I get to that number, I'm going to write just the factorial. The reason is because that will cancel out, right? The 2 factorials are the same. 28 factorial means 28 times 27 times 26, etc. And if I have the same thing on top and bottom, those will cancel out. So that's how I'm going to write that, because it makes it easy for me to cancel those things out. In the denominator, I cancel out the larger of the 2 numbers, and then I'm going to write out the smaller one. So 3 times 2 times 1 is 3 factorial. And then I'm going to just multiply that out. So in the numerator, I'm going to get 31 times 30 times 29, and that's going to give me 26,970. And in the denominator, 3 times 2 times 1 is 6. And then I would simply divide 26,970 by 6, and I would get 8,990. So you can see that compared to the permutation, the combination is much smaller. Okay, so you will memorize those formulas, and then the key is going to be figuring out what scenario you have. So your question they're asking is, does order matter or not? So our first example, how many ways can a 4-person student council be chosen from a freshman class of 125? So notice the student council is going to have positions, right? So the values are president, vice president, treasurer, and secretary. That means that order does matter, right? If you're chosen for president, you're going to be serving a different role than if you were chosen for treasurer. So order matters. If order matters, you use a permutation. So permutation, we have 125 people to choose from, and we're choosing 4 positions. So this is n factorial over n minus r factorial. So that's going to be 125 factorial over 125 minus 4 is 121 factorial. So I'm going to write the numerator as factors, so 125, 124, 123, and I'm going to keep going until I get to the denominator. So 121 is the denominator, so I'm going to write it as 121 factorial. And then remember what happens is the 121 factorials cancel, and I just multiply what's left up on the top. So 125 times 124 times 123 times 122, and that's going to give me a huge number. So 232,593,000. So that's the number of ways that they can choose a 4-person student council from a freshman class of 125. So the second one, how many ways can a 4-person committee be chosen from a group of 125? So notice the numbers are the same here. We're choosing 4 people to serve on a committee from 125 options. But also notice that it's a committee with no given titles. So there's no president or vice president. It's just 4 people serving on the committee. So we will assume that order does not matter because there are no titles or place values. So this one will be a combination. So it'll be a combination. We have 125 options and we're going to choose 4. So that'll be 125 factorial over 125 minus 4 factorial times 4 factorial. So this will be 125 factorial over 121 factorial times 4 factorial. Notice that the two bottom numbers, 121 plus 4, equal the top 125. Whenever you add up your factorials in the denominator for a combination, they should add up to the numerator. That's going to happen every time because that's the way the formula is set up. So now we're going to write the numerator as product, and you're going to keep doing that until you reach the higher of the two numbers on the bottom. So we're going to keep going until we get to 121, and then we're going to write it as 121 factorial. Again, that's so that the 121 factorials will cancel because they are the same. And then I need to write out the 4 factorial on the bottom. So 4, 3, 2, 1. I'm going to find the product at the top and the bottom. So I already know the top. That's what I got in number 1. So I'm probably not going to have room. Let me move down here. So 232,593,000 over 4 times 3 times 2 is 24. Okay, so now I'm just going to divide that out. And it looks like I got 9,600,000 691,375. So the key here is having the two formulas memorized and knowing that you use permutation when order matters and combination when order does not matter. All right, number 3. How many 6-digit passwords can be made using the digits 0 through 9? Part A is if repeated digits are allowed, and part B is if repeated digits are not allowed. So one thing I did not point out, which I need to do so, notice that for the formulas, this is without replacement. So these formulas only work if you do not allow replacement, meaning no repeats, right? No repeated values. So for number 3, if repeated digits are allowed, that means we cannot use one of the formulas. So we're going to have to do some kind of counting technique. 6-digit password, okay? So 6 things, right? 6 digits. They're saying digits 0 through 9. So that means there are 10 options, right? That's a common mistake is people say there are 9 options. But if you count the number 0, that gives you your 10th option. So that means there are 10 options for the first digit. We can repeat digits. So that means there are 10 options for the second digit. Since we can repeat, there are 10 options for every single digit of the 6-digit password. So this is going to be 10 to the 6th power. Another common one you'll see like this is they might give you a question about a true-false test. So you have 2 options on every question. And you can use repeated, right? You can use true more than once and false more than once. So you have 2 options for every question on the test. Or they'll tell you you have 10-question test and it's multiple choice with 4 options for each question. Something similar. So 10 to the 6th would be the answer. And if you want to know what it is, it would be 1,000,000. So there are 1,000,000 possible passwords if you're using 6 digits and you can repeat the digits. If repeated digits are not allowed, order does matter, right? Because it's a password. So if you type in the password, even if it's the same numbers in a different order, that's going to be wrong. So repeated digits are not allowed, meaning we can use a formula, and order matters. So it's a permutation. So the permutation, we have 10 digits to choose from, and we're choosing 6. So that'll be 10 factorial over 10 minus 6 factorial, which is 10 factorial over 4 factorial. So that's going to be 10, 9, 8, 7, 6, 5, 4 factorial. And I stopped at 4 and did the factorial because that's my denominator. So those will cancel out. Okay, and that will give me 151,200 possible 6-digit passwords that repeated digits are not allowed. So notice if we would have just done the counting technique where we did blanks and filled in the blanks with numbers, we would have gotten the same thing. We would have had 10 options for the first digit. Since we used one of the digits, we would only have 9 options for the second digit, and so forth. Okay, number 4. The Fight Club needs to select 3 men and 3 women to represent them in the upcoming tournament. If there are 12 men and 7 women who are members of the club, how many ways can the representatives be chosen? So it's important to note here that we're not just picking from one category. We have 2 totally different categories, right? If you're going to have men represent you and women represent you, you can only choose men from the possible men. and you can only choose women from the possible women. So you're going to have two different things going on. You're going to have one for the men and one for the women. So that's the first thing to keep in mind. So let's first just focus on the men, since that's what appears first in the problem. We want to choose 3 men to represent the Fight Club out of the 12 possibilities. Does order matter or not? So it might matter if they win, right? But all we're doing is choosing them to go off and represent us to fight. So that means the order does not matter. We're going to pick 3 people and they're going to go represent us. So that's a combination. So combination, 12 men, we're choosing 3. So that's going to be 12 factorial over 12 minus 3 factorial times 3 factorial. Okay, so that's going to be 12 factorial over 12 minus 3 is 9 times 3 factorial. We are now going to expand the numerator. So 12 times 11 times 10 times 9, and we're going to stop at 9 because that's the larger number from the denominator. That way the 9 factorials will cancel out. And then on the bottom we need to expand to the 3 factorial, so we have 3 times 2 times 1. All right, so 12 times 11 times 10 is going to be 1320. And then 6 times 2 times 1 is 6. So 1320 divided by 6 is 220. So that is the possible combinations of men, right? There's 3 possible combinations. There's 220 possible ways to pick 3 men from the 12. Now we want to do the same thing for women. So for the women, we still want to pick 3 women to represent the Fight Club, but we only have 7 members. So we only can pick 3 out of the 7 that we have as members. So this is going to be, again, a combination because order doesn't matter. We're going to choose from 7 options. 7 minus 3 factorial, 3 factorial. All right, so it's going to be 7 factorial over 4 factorial times 3 factorial. The larger number on the bottom is 4, so we're going to expand the top until we get to the 4. 4 factorials will cancel out. And then we're going to expand the 3 factorial. 7 times 6 times 5 is 210. 3 times 2 times 1 is 6. And then 210 divided by 6 is 35. So there are 35 ways to choose 3 women from the 7 possible women to choose from. We want to know how many ways the representatives of 3 men and 3 women can be chosen. So now we're back to kind of a basic counting principle technique where we know the possible options for men and we know the possible options for women. And so what we're going to do is we're just going to multiply those together. So there's 220 options for men times 35 options for women. So 220 times 35, and we get 7,700 possible ways to choose 3 men and 3 women from this Fight Club